Our next speaker is Alex Halderman. Alex is Associate Professor of Computer Science and Engineering at the University of Michigan and Director of Michigan Center for Computer Security and Society. His interests include computer and network security, internet security measurement, censorship resistance, electronic voting, as well as the interaction of technology and law and international affairs. His talk today is on applying data-centric security to constrained devices. Alex?
All right, thank you very much. Just give me 1 second so you don't have to look at a very smushed version of my presentation. Let me just try to guess the proper resolution for your projector. This is what I get for bringing my own PC. But as everyone can, well, that's close enough. As everyone can probably gather from that great introduction, I am a security native, and I come from the academic security world where we're concerned almost all of our time with attacks and defenses, with threats and countermeasures. And I joined the NDN project rather late in the game after the architecture had been laid down, but it's been just such a fascinating experience trying to think about how network architecture and security interact, to try to think about the potential for new architectural changes to just completely turn around the way that we approach security in areas like IoT. So my presentation today is going to be trying to bring a security natives perspective to looking at how architecture affects security and how NDN, thinking about security, can potentially be a very exciting way to improve our work on IoT. So you've all seen the NDN architecture so far. Hopefully people are familiar with this, so I won't go through it once again, but I'm going to try to keep my remarks relatively high level for people who are coming to this for approximately the first time today. Turn this off so you don't get echo. So in thinking about architecture and security, really there are a couple of different ways that you can approach developing a secure system. And the way that we in the security world often come to it is we start with properties, with requirements, with what we need the system to provide. You know, integrity, access control, privacy protection, and so forth. But as a security realist, looking at how systems actually get built and developed, I might observe that we get to define mechanisms. We don't get to define the future threats that our systems are going to face. That's largely up to our attackers or adversaries, and it's largely something that we can try to predict, but there's no guarantee that we're going to have complete control over it. So in NDN, we started by defining mechanisms more so than properties. And this, I think, is where the realist view starts to be important. So NDN begins with some seemingly simple architectural choices and concepts that ultimately turn out, not purely by serendipity, by a lot of great advanced planning, but not entirely in a predictable way either, to provide significant security leverage. And largely the research that I've been doing, the collaboration that I've been having with the NDN team has been about exploring the implications and applications of those core ideas to security. So my talk today is going to be about many of these implications. But since we do get to define the mechanism, starting from there and probing what kinds of security leverage we can get, gives us a foundation that we can be sure of in a way that we couldn't if we just were saying we need something that gives us integrity and access control, for instance, but we don't quite know who's going to attack it next. So In approaching NDN and security, the philosophy that NDN provides, of course, as you've heard from other speakers already today, is one of data-centric security, where the idea is that we're going to have as our atom that we're trying to secure, we're not going to be thinking so much about individual host systems as individual items of content. And we're going to get security by treating those items of content as things that have unique names rather than individual addresses, as in traditional IP networking. But already this transition from thinking about networking in terms of addresses to thinking about data, named data as your atom of security, starts to give you some significant security advantages. So in NDN, data is only going to flow, it's only going to move through the network in response to an interest request. And already this starts to change the game. So this reduces our attack surface because instead of being able to break in arbitrarily to host systems, the atom of data, of security, this piece of content that we're trying to protect can be individually secured. It provides resistance to some kinds of denial of service attacks, and I'll talk about that in a bit. And as you'll see, it provides some very interesting benefits for privacy. But in the NDN model, the thing that maybe took me as a security native the longest to wrap my head around was this idea of changing from securing the channel, as we do in the web world now, as we're trying to do with TLS, as a lot of my other research is about trying to improve the security of TLS that we rely on so ubiquitously in IP land. But changing from that model to one in which we're trying to secure the data itself also provides certain really interesting advantages. So securing the data is potentially lighter weight because you're dealing with data at rest rather than some kind of interactive cryptographic protocol between clients and servers. It's more friendly to networks that involve intermittent connectivity. And really, if you're able to secure the data itself, you no longer have to worry about so many translation problems when you're dealing with heterogeneous network environments. Right? If the data has been secured, if it's been individually signed or encrypted, then it can travel from one kind of network to another without worrying about security loss. So these are some of the properties that start to be so appealing when you think about network security for the Internet of Things, where we're operating with very constrained devices, where our connectivity can be at times very poor, and where we'd like to be able to be extremely flexible about how data is being transported. So the key way that we try to approach data-centric security in NDN is this idea that we're going to have a signature on every piece of data that's binding a name to a certain atom of content. All content must be signed in NDN. Now, this makes for another kind of very interesting transformation because it means that data can be stored in caches and routers within the network in a way where the attack surface of those devices is really very minimal. In a traditional host-centric model, we have to worry about people breaking into any of those devices. We have to worry about securing all of them from buffer overflows, from password compromises, and so forth that might potentially allow someone to get in and steal or change the data. But this data-centric model really converts that into a different problem. Because now, so long as we can protect a key in the device that's producing the content, that belongs to the publisher, then the data is going to be protected all the way until it's received by the client, regardless of whether the network in the middle is trustworthy. So we've converted the problem of host security, which is generally such a thorny issue, especially in the presence of the increasingly sophisticated attackers and nation states that we're worried about, into a problem that boils down to basic cryptography plus key management. Now, there's a saying in security that key management is the hard part of crypto, Well, that's true, but it turns out that crypto is the easy part of security. So this is already a big step forward for us. So we've thought a lot about how to implement signature mechanisms in NDN, and as you get more and more into the literature, into the technology that we've produced, there are a bunch of exciting ideas here. One of them is this idea that in NDN, since every data packet is signed, is binding a name to some content with a signature. Well, that's basically all that a certificate is in the rest of the world. So NDN provides this notion of something that works just like a certificate, essentially for free as a product of the architecture. Whereas in traditional IP and TLS land, we have these X.509 certificates that are this ancient, clanky format that causes endless problems for us in terms of parsing and extending it and so on. In NDN, a certificate is just another element of name signed data. So we can take a key, we can publish it as a data packet, and since it has a name and a signature, we have something that works like a certificate. This is really quite beautiful from a security perspective. Now, how we implement those certificates, those signatures, in a way that's efficient enough for resource-constrained devices, well, it depends a little bit on how resource-constrained you mean. RSA and ECD, elliptic curve-based signatures, are relatively cheap these days, but we're also exploring lighter weight mechanisms based on symmetric crypto and MAX, and the ways in which those might still be able to be validated by routers along the path in a network. So people who are operating on extremely constrained devices, we have you guys in mind too. Now, another thing that changes when you move from the TLS world to the world of signing data in NDN is this idea that you want signatures to be agile and to provide some security moving forward, even if the underlying keys, the underlying cryptography, age out over time. Right? Because we're no longer talking about an interactive authentication like in TLS, where you just need to know that the server you're talking to live really is who it claims to be. We want it to be possible for data to be published and signed and to be trustworthy for long into the future. So signatures do a lot of heavy lifting for us here too, but we've engineered other mechanisms to add to the robustness. Better mechanisms for things like status checking and figuring out whether a signature that's been made in the past is still good. Ways to include multiple signatures on a piece of content so that it can be vouched for once again if the original signature, if the original key or certificate is going to expire and so on. But we're learning a lot in trying to engineer better signature mechanisms that may also be applicable in the TLS world too. And so this is another place where it's very exciting. So another place that's useful for the TLS world too, but also for IoT and NDN, is an idea about how do you bootstrap trust? How do you automatically provision devices that are attaching to a network? And in the rest of my research focusing on the IP and TLS world, one project that has come out of this is something I co-founded called Let's Encrypt, that is a new certificate authority that is giving free certificates trusted by all major browsers to any site with a domain name. But as part of thinking about this in the context of an NDN future as well, we realized that we need mechanisms that can make provisioning trust, issuing certificates or their NDN equivalent into something that's essentially robotic, automatic, that attaching a device to a network, it can immediately gain some foothold of trust. And so we've developed protocols that are in use now by Let's Encrypt and also applicable in the NDN world that try to abstract the notion of verifying an identity, make it into something that can be done as robotically as possible and automate the provisioning of a certificate to a server or a device. so that becoming a trusted part of the network can be virtually automatic. Now, another idea, once again, that comes up again and again in NDN that may be difficult for people from the IP world to wrap their heads about is this idea that names and namespaces suddenly become such a powerful lever to use in defining trust relationships. So the simple questions like who is allowed to sign for what, we need some answer to. And one way to structure these kinds of relationships is just using the hierarchy of the namespace. So the namespace design itself can convey capabilities, can be a way to structure those trust relationships. Now, it's not always true that the logical way of structuring your namespace immediately maps into every important trust relationship for you. And after many conversations about this, we came up with this notion of trust schemas that schemata, as Ken put it very correctly, that are a more abstract notion of these trust relationships. The idea is basically that we want to define by policy a mapping from the structure of the namespace into some rules for how trust is to be applied and verified. And we can come up with templates for those policies that are predefined by experts, or applications can define them themselves. But to bring this back to the TLS world, right, if you're going to an HTTPS website, there's a static and simple relationship between a fixed set of routes and who is allowed to sign certificates for websites that you visit. But if you think about that relationship, it's just one of many, many possible ways of making a mapping from roots of trust to pieces of a namespace and what capabilities should be allowed. And trust schema are a wonderful generalization of all of this. It achieves vastly greater flexibility than things like the existing PKI. Now applications can define what those mappings and relationships should look like in a very general way. We've done other work thinking about how to optimize for performance in a world where signatures are such a key part, so to speak, of every interaction with data. And one way to do that, just to give you a single example, is about having producers of data provide evidence that the data was correctly signed up front, essentially bundling in the signed keychain with pieces of data that they're serving. And now the model that we're taking, this data-centric approach to security, enables optimizations like this without security loss. It enables the flexibility in the architecture, allows us to do these optimizations easily. So confidentiality and privacy is not something that we're going to get automatically just with signatures. And it's not really a part of the core NDN architecture at all. We made the architectural decision early on to leave it up to applications to figure out how confidentiality should be provided. However, that's not to say that the architecture itself doesn't also give us leverage here. One of the interesting things about NDN, as I said, was that data flows only in response to an interest request. And if it's found in a cache that's closer to an endpoint, then it's going to be delivered from there. So what this means is that if we have a network eavesdropper and they're spying on the network, say, close to a publisher or close to an intermediate cache that's not even going to be hit, they're not even going to see any data flowing in response to a request from an endpoint. They're only going to see it if they're close enough to the endpoint. And because these requests aren't associated with names, an endpoint that's just requesting content doesn't have the equivalent of an IP address. It's just going to be data following back a trail of breadcrumbs, essentially, to the endpoint that requested it. If you're anywhere in the network beyond the most local cache to that endpoint, then you're not going to be able to associate the data that's moving with who asked for it in the general case. And this is a potentially huge win for privacy. We've reduced the attack surface dramatically. Now, if we also want to maintain confidentiality of that data, of course, that's a challenge because it's going to be sitting in caches. It's going to be moving through the network in response to those requests. And so we take an old idea, this notion of using encryption as a means of providing access control, and we've abstracted it into this notion of name-based access control, where we use the hierarchy of the namespace to express fine-grained access rules basically about who can receive a key to decrypt a particular piece of encrypted data. So we are implementing mechanisms like this on top of NDN, but this is one way that we've explored to give applications back this control over confidentiality and access control to data while still allowing it to be maintained in these potentially untrusted caches and inside the network itself. There's ultimately a tension between cacheability and privacy, though, because if you have some piece of data that's in a cache and your adversary is, this is a cache close to the endpoint, and the adversary is able to be inspecting that, is eavesdropping on that cache, they can see that two clients, for instance, made encrypted requests and received back the same piece of encrypted data. That's not quite the perfect notion of confidentiality that we might want. But it facilitates a certain kind of trade-off between caching and extreme protection for privacy that may be very valuable in applications, especially those that are dealing with data that's being requested by many different clients and data that's going to otherwise be very taxing on the network. So there are new questions, there are new trade-offs that we need to think about in trying to secure and provide confidentiality and privacy protections for NDN, but they provide maybe some exciting new cost and benefit knobs that we can adjust. And we've been exploring many of these, as you've heard a little bit about some of our scenarios that we explored in the last, that we've been investigating. Things most close to IoT might be the enterprise building automation and management systems scenario we looked at. Where, again, we're trying to use the notion of hierarchy that's implicit in so many IoT systems, where you're talking about devices that are talking to each other within a room or a subsystem of a building, that are talking within a large campus, and so on. And exploring how those can best be addressed using these concepts from NDN. Now, through doing this, we've discovered for ourselves a lot of the wonderful things about working within highly constrained IoT devices. And so exploring things like using even lighter weight cryptography for command and data access control. And figuring out different, the many different ways in which hierarchy within an organization might map to devices in the field, not just physical location, of course, but the hierarchy of management within an enterprise, the hierarchy of maybe different realms of security within a highly secured environment. But things, notions like the trust schema notion, notions like name-based access control have proved very fruitful here, as we can explain more. But I'm almost out of time, so let me give you just a few takeaway lessons from all of this, from my perspective as a security person looking at NDN. So this philosophy of data-centric networking allows us to convert hard security problems like securing hosts into problems that are relatively easier. Crypto, key management, things that we do have good principled tools to deal with. This is, to me, one of the most exciting things about the entire project. But at the same time, security from an architectural standpoint, when you're defining the network architecture de novo, gives us this opportunity to lay down mechanisms that will survive even as our security priorities continue to evolve, and gives us a solid foundation. So I think the mapping between some of these properties I've talked about that NDN provides and the needs of IoT is just this great opportunity because this allows us through NDN to lay down some building blocks for secure applications through providing a data-centric means of integrity protection, of access control, and of confidentiality that I think can greatly simplify many of the applications and challenges that we're trying to solve today. So thank you very much, and I'm here all day. Thank you for coming out, and thank you to NIST for hosting us.